Creationists love to talk about Mount St. Helens as a monument to catastrophism, but nothing could be further from the truth. Tectonic subduction of the Juan de Fuca plate continues to fuel volcanism in the Cascade Range of the Pacific Northwest. The 1980 eruptions of Mount St. Helens were the deadliest and among the largest in modern American history. Nearly half of the mountain's summit was ejected into a massive cloud of ash which swept across the adjacent forest and towns. Melting of the snowpack led to catastrophic flooding and sediment-choked mudflows which buried whole trees in minutes. If you're at least 50 and called the Pacific Northwest home, you may remember this as the morning you woke up to a thick snowfall of apocalyptic ash. Cars and streets were covered in it for days. But if you've spent any time interacting with Young Earth Creationism, you know that Mount St. Helens is one of the most widely cited examples from geology put forth in support of their worldview. In the early 1990s, Dr. Stephen Austin, a geologist who at the time worked for Henry Morris's Institute for Creation Research, would document the features adjacent to the volcano. He would argue that the rapid deposition and erosion at Mount St. Helens provides an analogy for understanding geological history in the context of Noah's flood. In addition, he would collect rock samples that formed during the eruption and send them off for potassium argon dating. These results, according to creationists, give us ample reason not to accept millions of years. Since the rock samples were only a decade old, their radiometric ages should have been essentially zero within margin of error. But that wasn't the case. All of them contained measurable argon, according to Austin, so the ages were wrong by hundreds of thousands of years or more. This led to one of the most popular mantras in creationism today.
If radiometric dating doesn't work for rocks of known ages, why do we trust it for rocks of unknown ages?
Austin's claims about rapid deposition are worth discussing, but I want to save them for another time. In this video, I will focus on the second point and take a closer look at this paper published by ICR in 1996, which summarizes the potassium argon dating of Steve Austin's samples. If you're not familiar, here's the story. The 1980 eruption resulted in the formation of a new lava dome which solidified around 1986. Austin collected samples which he identified as dacite and then proceeded to apply some basic treatments to separate the rock into its mineral components, namely feldspar, amphibole, and pyroxene. He then sent the samples to Geochron, a commercial laboratory in Massachusetts, and asked them to perform potassium argon dating. According to Austin, he did not provide any information about the origin of the samples, except to say that they were relatively young. Austin's dating results are given in Table 3 of his publication, ranging from 350,000 to over 2 million years old. And to be fair, if you saw these results without any background, it would be reasonable to conclude that we can't trust radiometric dating. It's understood that science has a margin of error, but these ages are clearly way higher than they should be. However, if you were to show this table to a geochemist, even one who doesn't regularly work with potassium argon data, they would be quick to point out a few things wrong. First, where are the uncertainties? Every column here should have a plus or minus. But only the final ages have a reported margin of error without even specifying the confidence level. Is it 1 sigma or 2 or something else? In addition, all of the constants used have been updated since 1996 due to more precise measurements with better technology. Before we even get to the calculations, I will show you that even if we assume that Austin's ages are perfectly sound, they are actually consistent with the known age of the eruption and thus disprove the young Earth timeline. That seems counterintuitive, but it only takes a little background in the geology of the site. However, we shouldn't take Austin's results at face value because he failed to report and propagate the analytical errors when calculating the age. Therefore, they are fraudulent. Finally, Austin chose a lab that used the wrong technique for measuring trace argon in recent volcanics, so his reported ages and claims of excess radiogenic argon aren't even real. So what do I mean by saying that Austin's ages could be correct even though the rock was only 10 years old? Take a look at the breakdown of minerals from youngest to oldest. If you take an intro geology, you may recognize that toward the top of the list, the minerals become more mafic and form at higher temperatures. This is essentially Bowen's reaction series, which describes the order in which minerals crystallize from a cooling magma. In other words, the pyroxene should be older than the amphibole and most feldspars. Although most of an extrusive volcanic rock forms as lava solidifies, there are commonly larger minerals or phenocrysts that were already formed at the time of the eruption. Remember, the source of the lava is here, magma chambers within and below the volcanic range. But magma is not pure liquid rock, it's a mixture of the liquid melts and the solid mineral precipitates. In a stratovolcano like Mount St. Helens, eruptions have to break through thick layers formed by previous lava flows, during which the lava may assimilate older material called xenocrysts. So, not all of a brand new volcanic rock has an age of 0. Individual minerals can be much older, even by millions of years, depending on the setting. Therefore, Austin's results can be split into two fuzzy categories, one that mostly contains components that formed during or after the eruption, and another that mostly contains components that formed well before the eruption. We have evidence of this fact from Austin's own image of the sample in thin section. Do you see the pretty lines here within the feldspar grains? It creates this alternating color scheme. This is called zoning, and it occurs when there is variability in the calcium and sodium contents of the magma chamber. It causes two phases of plagioclase feldspar, albite and anorthite, to grow concentrically. Zoning of this size cannot form during the post-eruptive cooling stage. Because mineral growth rates are well monitored and documented in the new lava dome from 1980 to 1986, we can confidently say that these large grains of feldspar are not only 10 years old. In other words, the ages of Austin's dacite samples are not the same age of the eruption. They are mixed ages of a long geologic process. Therefore, Austin's potassium argon ages are entirely reasonable for a recent eruption at a stratovolcano like Mount St. Helens. If we wanted to use potassium argon dating to find the age of the eruption itself, we wouldn't use the mineral separates in the whole rock value. Rather, we would avoid large phenocrysts and inherited xenocrysts by analyzing only the volcanic glass or things like sanidine, which is standard in the field. That being said, we should not accept Austin's results at face value. And you may be wondering, can we really take a brand new rock and send it to a lab for radiometric dating and expect reasonable results, especially when that lab explicitly warned that they can't handle samples that are younger than 2 million years old? And if we can't, does that mean that the potassium argon method can never really be tested empirically? That's a fair question, which too often is ignored. I don't want to do that here, and we will come back to it. There are two reasons commonly given for why Geochron Labs couldn't date young samples, and thus we should reject Austin's potassium argon ages. First, that insufficient time had passed for enough argon to accumulate in the sample, and since the argon couldn't be measured, it won't give an accurate age. Second, that dating a sample this young is like trying to measure grains of sand on a scale built for people, and you can't do it. It's the wrong equipment for the job. Although both of these statements have a semblance of truth, they are ultimately incorrect and misleading if they lead us to conclude that potassium argon cannot be empirically tested with samples of known age. In fact, there are many examples of potassium argon dating being successfully used to date historically constrained eruptions with high precision. Even in 1994, it was possible to date samples of Holocene or Pleistocene age, which, in terms of their argon content, aren't that different from those rocks at Mount St. Helens. To illustrate this point, consider the equation for electron capture decay from potassium-2 argon, which has a half-life of 1.25 billion years. To determine the age of a mineral, we need to calculate the ratio between 40 argon and 40 potassium. If you have plenty of both, that's not so hard to do with precision, but what if no time has passed and there is no argon? Well, then your scale will read 0, or so close to 0 that you can't tell the difference. If you plug in 0 for argon in this equation, the parentheses become 1 plus 0. The natural log of 1 is 0, which multiplied by anything is 0. That's your age, which is accurate. In short, if your scale isn't sensitive enough to distinguish parts per trillion levels of argon isotopes, then you can't tell the difference between 0 years old and 1,000 years old, but you will get an age that's within error of 0. It's not like samples will date to 500 million years old if they're really, really young, but suddenly the age is accurate if at least 2 million years has passed. On the contrary, ages should still be accurate in young samples, albeit with very low precision. In classic potassium argon dating, that margin of error increases exponentially as you approach 0, exceeding 50% in very young samples. To understand why this happens, we first have to point out the obvious. Our cartoon schematic is not how potassium and argon are weighed in the rock samples. The disadvantage of classic potassium argon dating, which Austin used, is that the solid potassium and noble gas argon have to be measured separately. Potassium is analyzed on a flame photometer, which gives you the percentage of your sample that is potassium oxide. After converting this to parts per million potassium, you can multiply the concentration by the known isotopic abundance of 40 potassium, which, as you can tell by the times 10 to the minus 4, is a rare isotope. This product gives you the denominator in our age equation. Because argon isn't bonded in the mineral, it can be extracted from the sample in high-temperature furnace under a strong vacuum. The extracted gas is then sent to a mass spectrometer, which ultimately determines both the argon concentration and the ratio of 40 argon to 36 argon. Using what's called the isotope dilution method, these ratios are measured precisely by adding what's called a reference spike. In short, this is how we tare and calibrate the scale. Finally, because argon is everywhere, we expect there to be some amount of atmospheric argon in every analysis, including the sample. That's not a problem because we can subtract it from the measurement as long as we know the 40 to 36 ratio of atmospheric argon. Radiogenic argon, 40 argon with the asterisk, is equal to 1 minus N divided by the measured 40 to 36 argon ratio, where N is the ratio in atmospheric argon. You can try this equation yourself. If our sample has a 40 to 36 ratio equal to that of the atmosphere, then N is divided by itself, which is equal to 1. 1 minus 1 equals 0, which is the amount of argon in your sample that came from radioactive decay. If our sample has a 40 to 36 ratio that is double that of the atmosphere, then we get N divided by 2N, which is 1/2. 1 minus 1/2 is 1/2. So 50% of the measured argon came from radioactive decay. By multiplying the fraction of radiogenic argon by its concentration, you get the numerator in the age equation. Put these together and you can determine the model age of the sample, that is, how long the system has remained closed. Soon after the potassium argon method became standard, the argon-argon method was developed to address some of its shortcomings. With classic potassium argon dating, each element has to be measured separately, which can require larger samples and introduce new analytical uncertainty. The radiogenic argon content is calculated by subtracting the atmospheric argon isotope ratio, but if some argon was trapped in the mineral with a ratio different than that of the atmosphere, it artificially yields a higher age. Finally, due to all these factors, potassium argon ages become imprecise in very young samples, with 1 sigma exceeding 50%. With the argon-argon method, however, potassium is converted to argon in a nuclear reactor, which allows us to measure all isotope abundances on the same mass spectrometer in the same analysis. That alone improves the precision. These ratios are then calibrated against reference standards of known age, including some historical samples. Thus, excess argon can be identified and corrected for if present, which allows for high-precision analysis of young samples. So based on this comparison, which method would you choose to date a rock from Mount St. Helens? And yes, both options were widely available in 1996. Well, that's not what Austin did. He chose the method most likely to yield imprecise, if not erroneous, results. That being said, if we look at the errors reported in Austin's data table, they're not that bad. 15 to 20% is not great, but good enough for government work, as the saying goes. Actually, they're suspiciously good enough based on the overview I just gave. How is that possible? When I went to reproduce Austin's age calculations from his data table, I discovered that the error bars are completely fabricated. Or at least, they don't account for the sum of all uncertainties involved with the method that he used, which, as far as I can tell, makes them fraudulent. To understand why, let's review the concept of error propagation, which I promise is not as bad as it sounds. Say that we have a value A that is calculated from two other observations, B and C. Perhaps A is the total concentration of two substances. But when we measure the concentrations of B and C, each of those observations has its own margin of error, plus or minus some value. So what is the total error in A if A is calculated from B and C? This is called the propagation of errors, and the formula depends on the mathematical operation used to combine the variables. If A is the result of addition or subtraction, then the error in A is the square root of the sum variances, kind of like calculating the hypotenuse of a triangle. If A is the result of multiplication or division, then the error in A is A times the square root of the normalized sum of variances. So using these simple rules, we can propagate the errors from all variables in the potassium argon equation, and it's, oh dear God, what is that? Alright, perhaps I should have titled this How to Lose Your Audience in a Single Slide. But alright, nobody panic, we can do this. But in all seriousness, however messy this equation looks, there is no complex math here. It's really just a matter of plugging in all the right variables, which are measured on the mass spectrometer. U, V, and W are the uncertainties associated with each isotope of argon, and X is the reference spike added to your sample. Once you have those, anyone could type this formula into Excel and just press enter. The only problem is that Austin didn't publish these values, so we have to get a little creative. We can simplify this formula so that it uses errors associated with the isotope ratios rather than individual isotopes. That's helpful because these errors are generally known for this type of analysis based on surveys by the USGS. And the value of R is published in Austin's table, in the third to last column. So we can just plug that in directly. On the right here are the typical errors expressed as percentages that we'd need to consider in calculating the age uncertainty. The important ones are highlighted in red because they contribute the most to the overall variance in a young sample with almost no radiogenic argon. The rest have negligible impacts unless your sample is either very old or super low in potassium. Based on those published surveys, typical 1 sigma errors are 0.2% and 0.5% for ratios Y and Z respectively, and 0.3% for the spike calibration. That's what I used in the formula on the previous slide. Now, here are Austin's original reported ages and error bars. It's very reasonable to conclude that the radiometric age of the dacite is well above the known age of the eruption and thus must be wrong. However, when we plot the ages with their true uncertainties, it's far less convincing. Now the whole rock, feldspar, and amphibole ages are plausibly within range of zero. The pyroxene in particular, which forms at higher temperature, has a higher closure temperature, and can more easily capture radiogenic argon in the magma, still yields the highest age, as expected. Importantly, we should ask, why didn't Austin publish these data with the fully propagated errors? As far as I can tell from the manuscript, his error bars reflect the average of 2 values for each sample, but if you do that in a real publication, you have to report those 2 values as well as their individual uncertainties. This is poor practice scientifically and has misled a generation of young Earth creationists into believing these data actually support their claims. They don't. At best, these data show that conventional potassium argon dating gives reasonable results for modern samples, but with super low precision and high errors if you don't pay attention to the basic principles of igneous petrology. They also suggest that if we could apply the same method to these rocks after 100 million years have passed, the potassium argon age should be within error of 100 million years. We have no reason, based on Austin's own work, to be suspicious of radiometric dates that are orders of magnitude greater than, and thus disprove, the Young Earth timeline. But the fun doesn't end here. Oh no, it gets much worse. Because Austin chose a lab that used the wrong analytical technique for potassium argon, it's not only the error bars that are wrong, the ages themselves are meaningless. Before I get to why, we really need to address this guy's question. Unfortunately, the two are connected. So, can we actually test the potassium argon method on samples of known age? With error bars in the hundreds of thousands of years, it would seem like the best we could hope for is a terribly inaccurate age that happens to overlap with zero. If your impression is, hey, that's not much of a test, well, you're right. But most of the error bar derives from the extremely low radiogenic argon fraction in Austin's samples, combined with a 10 times higher than normal argon concentration, which is an artifact of using the wrong potassium argon method. And I don't mean potassium argon versus argon as discussed previously. I mean the wrong analytical technique for potassium argon dating. You see, Geochron Labs used what's called the isotope dilution method to measure how much of each argon isotope was in Austin's samples. Every sample has a mixture of 3 isotopes, 40, 38, and 36 argon. The relative heights of these bars are the unknowns we want to determine. If the ratio of 40 to 36 is the same as the atmosphere, your sample is estimated to be 0 years old. The older the sample gets, the more radiogenic argon it accumulates, so the height of 40 argon will grow. After millions of years, the 40 argon bar becomes thousands and thousands of times larger than the others, so it kind of swamps them out. To determine not only the ratio of each isotope but the total abundance of argon, we need some kind of standard to compare it against. Isotope dilution uses what's called a reference spike, or a synthetic mixture of argon isotopes made from adding pure 38 argon to a small volume of atmospheric argon. A known amount of spike is then combined with your unknown sample argon, and this mixture is what's measured on the mass spectrometer, specifically the ratios of 40 to 38 and 38 to 36 argon. Deviations from the reference spike, which can then be subtracted mathematically, give you the isotopic ratio and concentration of argon needed to calculate the potassium argon age. This method is highly accurate and standard practice in many radiometric dating methods. However, what would happen if your sample is young or even 0 age? In that case, the tiny bit of argon present should have close to the same ratio as the atmospheric argon mixed with the spike. So when we go through this exercise of spiking the sample, measuring the mixture, then subtracting it back out, the actual argon levels are effectively drowned out by the spike correction. It's nearly impossible to tell the difference between something that has the same ratios as the atmosphere and something that is aged only a few thousand years or even a few million years. In other words, these results reported by Austin, where the fraction of radiogenic argon is absolutely minuscule and way below what this method can accurately resolve, they're not even real. That's why the error bars, the real error bars, are so unusually high. Fortunately for geologists who care about doing this right, there is a third option here that can precisely resolve those tiny deviations from atmospheric argon in young and even 0-age volcanic samples. It's known as the Cassignol technique, after the French geochemist who developed it. The first step is to remove the reference spike entirely, hence it's also called the unspiked Cassignol method. Instead, we want to compare the isotope ratios in our sample directly against atmospheric argon. In mass spectrometry, it's highly important that these gases are at the same conditions, meaning temperature and pressure. So the sample volume is amplified and carefully adjusted by taking repeat aliquots of argon from the mineral. Then, the reference gas is taken stepwise from a diminishing volume of atmosphere, so that at every iteration, the comparison between the two is slightly different. The isotopic data from this stepwise analysis will follow along a regression line which both accurately and precisely points to the true argon isotope ratio in your sample when the volumes are matched perfectly. As a result, those tiny fractions of radiogenic argon are easily resolved, and you can get ages like this one, 14,000 years plus or minus 3,000. And you can document the individual ages of successive volcanic eruptions on Mauritius over the last 150,000 years, as an example. That's a massive improvement over what we see in Austin's data. Or take this paper by Guillot, who co-developed this method, and Yves Cornet. I'll link it in the description for those who want to read further, but the article both summarizes the unspiked method and demonstrates that it consistently replicated historically known ages of volcanoes less than 3,000 years old, and with only a couple centuries uncertainty. That is incredible when you think of how low the radiogenic argon is in those samples. In addition, they showed that the unspiked potassium argon ages consistently replicated independent ages from both radiocarbon and thermoluminescence. That is, the linear relationship in the figures on the right. Now, I know what you're thinking. This technology is impressive and so are the advancements in the field, but Austin did his research in 1996 and he could only use what was available at the time, right? Well, sure, except this paper was published in 1986 and the Castagnol method itself was developed in 1982. It was widely available in 1996. Austin had no excuse for sending those samples to a commercial lab that used isotope dilution methods, unless he wanted to get a meaningless result. Now we get to our final point, which is that Austin's ages assume, without justification, that the initial 40 to 36 argon ratio of the lava dome was exactly 295.5. Of course, he is not unaware of this fact. It drives his main point and conclusion, which is that volcanic rocks have some non-zero amount of radiogenic argon when they form, and therefore our model assumptions are wrong and you can't determine their true age. First, this observation is far from being novel. It was well documented since the 1960s that sometimes, not most of the time, but rarely, volcanic minerals can inherit non-zero amounts of radiogenic argon, and thus give apparently old ages by up to a couple million years. Does that mean we have to keep assuming blindly and can never correct for the true initial argon ratio? Of course not. That's why the argon-argon isochron method was developed. It allows us to measure the initial 40 to 36 ratio by proxy, so we don't have to just sit around and make guesses or give up on geology. In fact, this technique has been extensively applied to recent volcanics from Mount St. Helens, specifically to lavas less than 4,000 years old. And it was found that for the felsic dacites, like the one Austin collected, the initial argon is close to, but not exactly the same as, atmospheric values. Importantly, that ratio is slightly higher in the mafic fractions from the same felsic dacite. If we look at an isochron from a Mount St. Helens dacite with similar chemistry to Austin's sample, the initial argon ratio was 298.7, not 295.5. That may not seem like a big difference, but look what happens to Austin's ages when we adjust for it. Here are the original data, and here they are recalculated for the updated value. With the exception of pyroxene, all of Austin's samples are now indistinguishable from 0 years old. In other words, ICR's dating of Mount St. Helens gave the known age of the eruption despite their best efforts not to. They spent a few $1,000s just to validate radiometric dating and discover things that have been known from the 1960s. We can repeat this exercise for the mafic fractions based on observed data from Mount St. Helens. Assuming a middle range value of 306, those ages become indistinguishable from 0. If you want to know why creationists never had any impact on the scientific community, it's not a conspiracy and it's certainly not an attack on their faith. It's that all their so-called research only supports what we already know. So perhaps it's time to update the mantra. How does it go? Since we can trust the results of samples of known age,
and if radiometric dating work for rocks of known ages, we trust it for rocks of unknown ages.
Thank you all for sticking around, and I'll see you in the next one. Don't hesitate to leave your thoughts and questions in the comments, and please share this video with anybody who believes that Mount St. Helens is a monument to young Earth creationism.